The recording. Okay. Hello, everyone. Welcome to this session of the FGC IPM Nonlinear Theory webinar series. Today's speaker is Dr. Ali Mohammadi from IPM, and he will talk about bounds on point-conic incidence over finite fields and applications. Dr. Mohammadi, you may start your talk whenever you want. The time is yours.
Okay, thank you very much, Abbas, for the introduction, and thank you and Semi, the organizers of this seminar, for inviting me. And thanks everyone for coming, and especially it's a great pleasure to see Igor and Bryce. Igor was my supervisor in Sydney, and Bryce is a very long time friend. He's been my friend since pretty much the first year of university. And yeah, I hadn't seen them for a long time, so it's really nice to see you today. So yeah, the talk will be about bounds on point-conic incidences over finite fields, and I'll also consider one application. There are a lot of number theoretic applications of this type of bounds, but I thought maybe it's not so suitable for this seminar, which is more algebraic geometric. So the ideas will be mostly very simple and very geometric. So we use F to be an arbitrary field, FQ a finite field of order Q and characteristic P. So Q is a power of P. FPD be the d-dimensional projective space over F. And sometimes we interchangeably switch between F2 and just this restriction to the two-dimensional projective space. And D generally will be just 2. And P is squibbly, P will be the points, L lines, C curves, which in this cycle will be generally conics, and these will be over FD, which generally will be, D will be generally 2, except just a little bit at the end of the talk. And both lowercase letters, P will be points. I just did this just because we have too many variables. So I mean, P, we also have characteristic. And we also use standard asymptotic notation. A double LB means that there is some absolute constant so that A is less than or equal to CB. A and B generally will be some sequences. And the same as this. But you know, the absolute constant, of course, will be different from slides to slides. So to introduce the problem that we'll be talking about, let P and C be some sets of points and algebraic curves over some arbitrary field. Then the number of incidences will be the two tuples P and C of points and curves, so that P sits on C. So say if you have two lines crossing each other, and at that intersection you have one point, this would amount to 2 incidences. And conics will be defined by let phi be some 3-variable polynomial. It should be homogeneous, as in each monomial has degree 2. So you know, xy plus y to the 2. Sorry, xy plus y to the 2 plus xz and so on. But the restriction of this to the so the number of solutions of this with x coming from the two-dimensional projective plane will define a conic. And we say it's irreducible or non-degenerative. You can't write it as a product of 2 degree 1 polynomials. And yeah, this talk will be pretty much just about bounding the number of incidences between points and conics over FP2, where P is a prime. Pretty much everything I'll talk about will also work on arbitrary fields, because the tools we use also work on arbitrary fields, but it's just easier to, I mean, first of all, people really just care about these over finite fields. And so I mean, we just restrict our attention to finite fields. So firstly, what do we know just combinatorially and using nothing about the fields. Consider, I mean, we recall the result, which really was just about graphs. If you consider the incidence graph of P and C, so it's a bipartite graph, and there is an edge if there is an incidence between P and C. If this doesn't contain a copy of the complete bipartite graph KST, as in for any S points in P, there are fewer than T curves in C incidence to it, then you have such a bound. And like I said, it just uses combinatorial facts. And it's not quite trivial, but it's generally referred to as a trivial bound. And the rule, because, like I said, because it's really just a graph theoretic statement, the rules of P and C and S and T could be switched. So for example, if you write PCI for the incidence graph between PC, then if you're just thinking about lines, this graph doesn't have a K22, CPI doesn't have a K22, PCI no K52. I will explain this on the next slide, but mainly maybe just pay attention for now to these numbers, that the fact that PCI has no K22, so S is 2, we don't actually care about this T to the 1 on S because it just gets absorbed as a constant. Also not about this S, mainly about this thing. So, so for general irreducible conics, one trivial bound will be just P times C to the 1 minus 1 on 5. And for circles and parabolas, 1 minus 1 on 3. And again, for circles and parabolas, if you switch the role of P and C, here you would have a 1 minus 1 on 2. I mean, if you look up any paper on incidences, especially Semeridi Trotter, you will see the trivial bound, a simple proof for lines, point lines. And really the idea is to just write IPC as a double sum of an indicator function of a line with variable taking points, and with just application of Cauchy-Schwarz and using the fact that two distinct points have only one line going through them and two distinct lines can meet in at most one point, you can easily prove such a statement. I don't know what how this more general statement is proved. Probably using Holder. I mean, you could use Holder, but it would look like a nightmare. So like I said, two lines over the plane meeting at most one point. This gives you this thing. So two lines can meet in at most one point. So there is no K22 in this incidence graph. Also, for any 2 points, there is at most one line passing both. It gives this one. So if you take 2 points, there is at most one line. So it has, again, no K22. And it gives this bound. It's very important to note that when P and L have the same size, then you get this n to the 3 on 2. These minimum of these two terms come to n to the 3 on 2. So for a general irreducible conic, it is uniquely determined by 5 points. So it means that if you take 5 points and there are two conics passing through these 5 points, it must be the same thing. So no K52. Also by Bezout's theorem, any two distinct conics means at most 4 points, so no K25. And it gives this bound. For parabolas and circles, you still use Bezout, but the thing is, for example, the fact that two conics meet in at most 4 points, it really turns out that two of these points are at infinity, but we care about the plane. So two unique circles really meet in at most 2 points, and also three points uniquely determine the circle. So you get this bound. Again, these are not exactly trivial, but for example, for most number theoretic applications, if you start using these, yeah, you don't get anything. And also over the reals, you can actually just use these very basic. There are strong lemmas where you can actually use these type of information about sets of curves and points to get really strong bounds. But you don't have anything like that over finite fields. So what is known for incidences? Over the real plane, Mohammadi Trotter in 1983 proved P to the 2/3 and L to the 2/3. And this was extended to C2 by Toth in 2015. So I didn't actually realize this until last night. It took a really long time just to extend it to complex plane. Over FP2, it took almost 20 years for Borg and Katz-Tau to get the first non-trivial result over finite fields. And like I said, if you remember, we said 3 on 2 is the trivial bound. And say if you're working over FQ, so general finite fields, and you take your point set to be the Cartesian product of 2 subfields, and L also the dual of the same Cartesian product, then both your point set and line set will be of size G to the 2 if your subfield is G. And you can easily show that the lower bound is G to the 3. So this N to the 3 on 2 is actually easily achieved. So a very necessary condition over finite fields would be to make sure your point set at least doesn't hugely correlate with the affine image of these Cartesian products of subfields. So if you're just working on FP, that just says that you don't want your point set to be the whole plane, which is this condition. So it needs to be of size P to the alpha. Alpha is strictly less than 2. But like I said, over FQ, it gets a lot more complex. And also another point, they gave no explicit value for epsilon. And a series of authors made this explicit. I think the best bound was by Jones based on this method, and maybe 1 on 400 or something like this. But relatively recently, Stevens and Desiu got what is now the best known incidence span over finite fields. It is actually over arbitrary fields. And if the arbitrary field has characteristic P non-zero, then you need to put this condition. Again, this translates to asking that P is in the whole plane, finite plane. And also notice that they have this restriction that P and L really need to be pretty much the same size. In this case, they proved this bound. And in the same paper, they proved a substantially better bound for Cartesian products. It still comes fairly short of Mohammadi Trotter. And they actually used that to deduce this bound. Basically, the idea is that if you have a point set and which has too many incidences, you can subdivide it into a lot of Cartesian product looking sets and individually apply the Cartesian product incidence band to these and add them up. It's a very nice idea, but it's a very inefficient way. Actually, one of the main motivations for this project was to avoid this step. And their result is actually based on a point plane incidence band of Rudnev. And I mean, our goal was to see if we can go from point plane to point line more directly and not do this Cartesian product then general point set. But I think there are really good reasons why this might not work. Also, for a comparison with trivial bound and sharp bound, so n to the 4 on, there are examples showing n to the 4 on 3 would be sharp. And what Stevens Desiu give is n to the 3 on 2. So it's a saving of 1 on 30 over the trivial bound, but it's still 4 on 30 away from the sharp bound. So it's about 4 times further from its improvement over the trivial band than it is to getting to the sharp band. So a lot of room for research in this problem. And there are a serious number of applications for such a result. So it's very desirable to improve this thing. Also, the point plane incidence of RootNef as well. It was as part of this project that we realized this point plane incidence of RootNef also works best around where the plane set and the point set have about the same size. The bound is number of planes times square root of number of points plus some error term not allowing too many collinear points in your point set, because that could lead to a lot of degenerate. You could have a lot of planes passing through that line. So you need such a condition. And also there are other results by Win in 2011. This thing works only for large sets. So you can check, and it only becomes non-trivial when P and L are of size larger than Q. And also it's worth noting that this thing is around the expected average. So a single line occupies around 1 on Q of your whole plane. So the odds of your points meeting the expected value of your incidences becomes P times L times this 1 on Q. And this would be the error term. I think this should be, in the upper ranges, this becomes optimal. I think when P and L are around Q to the 3 on 4 or maybe 2 on 3, you can easily calculate. And more generally, in the same paper, you also proved incidences for points on hyperplanes. So, if you set D to be 2, you get the first thing. Also, in that paper, you actually got a logarithmic dependence here. So I'm cheating a little bit to say they were from the same paper, but in a later paper, he dropped he made this less than or equal. For nonlinear incidences over FV, very, very, very little is known. So first of all, they were having mostly about Mobius transformations. A Mobius transformation is this mapping AX plus B over CX plus D. A, B, C, D are in GL2 of FB as in non-zero determinant. And the first one came from Bourgain in 2012. He proved a non-trivial bound for number of incidences between a set of Mobius transformations and points over FB. It's non-quantitative and doesn't really give much of a clue how to quantify it. And it may be actually, although it is non-quantitative, it still may be the most general such bound that allows a large class of Mobius transformations. Shkredov in 2021 proved such a bound for Mobius hyperbole. These still belong to these Mobius transformations. And so 2 parameters defining these points, and these parameters must come from Cartesian products. So still not a great deal of progress in allowing some variation on your curves. But the point was, this was quantitative, fairly strong. Rudneff and Wheeler, first of all, obtained a quantitative improvement. Secondly, they proved a different bound, allowing A and B to come from more general sets. This is just from a few months ago. And actually, the ideas here very much are the root of our project. And also, right after it, Wheeler and Warren being one of the co-authors of our paper, proved a quantitative incidence band for Mobius transformations. So this time 3 parameter curves. So up to Rudneff and Wheeler, it was just 2 parameter curves, just A and B, say. So we took, so this talk will be about point-conic incidences, and let's give a very quick warm-up. So let's see the parabolas of this form. Sorry, I'm saying. Incidence relation in case of Mobius transformation means what exactly curve defined by, I'm not sure exactly what the question is.
Just in the previous slide, when you were mentioning incidence relation between Mobius transformations, between points and Mobius transformations, I mean, we looked at incidence relations for curves. So are we forming a curve by x comma its Mobius transform and then looking at that incidence relation, or are we looking at curves that remain invariant under the Mobius transform?
Oh no, this thing defines a curve. So let fx be just y. You know, write it in a non-rational, and this defines a curve, right?
Yeah.
And also,
so x comma fx, and maybe 1 being the coordinates of the point, the graph of the Mobius transformation.
That's it. Yeah, that's it.
Yes. Okay.
And also, you have to be careful, right? Because these are coming from GL2, and scalar multiplication gives the same Mobius transformation. So really, you want to fix, for example, one of these things. In later in talk, we'll fix C to be 1. So these are really 3-parameter curves.
Okay. Yeah. Oh, but if we fix one of them to be 1, then we omit the portion where it is 0, or that's still, oh, okay.
No, yeah. It's still a curve, 2-variable curve, and yeah,
okay.
I mean, really, the only problem was not allowing multiplicity, right? Because if you time everything by, say, lambda, the lambda really cancels out.
Yes.
Yeah. That's the only point I was making. Otherwise, yeah, the curve will be like we said first. You just write this y equals to ax plus b and bring cx plus d over here. Yeah. Okay, yeah, so we want to take a step further and sort of look at some other curves. And so starting, I mean, the project was about conics. And so let's just see a very simple example that is a sort of a warm-up for what we do later. Let y be x to the 2 plus ax plus b. So this time, this is 2 parameters defining these parabolas. But, you know, generally you would have y equals ax2 plus bx plus c. Now, just apply this mapping that sends xy to x, y minus x to the 2. And it's fairly simple to check that it's a bijection. Also, it maps these parabolas to lines of the form y equals ax plus b. And basically saying that P sits on this CAB if and only if the map of P sits in this LAB. So basically what we have said is that we can easily transform the incidence problem between these parabolas and points to a point line question. And it's fairly simple to see that the size of the line is the same as the size of the parabolas, and the size of P remains the same as well. So you just apply point line. So no loss in strength. And the theme of basically all progress to nonlinear questions over finite fields really is just reducing your point curve incidence to a linear one. But here there is no loss. The later techniques we'll see there is a fair bit of loss. And this idea was by Pham, Nguyen, and Desiu in 2018, and they proved really interesting results based on this fairly simple observation. So what we proved was that if C is a set of irreducible conics over Fp, and P is a set of points, again, as always, we need some condition not allowing P to be the whole plane. Then we proved non-trivial bounds. one point is that if you recall, we had these trivial bounds, and if you compare them with this thing, it shows that in this range we get a non-trivial bound. So basically, C has to be fairly large, which makes sense. I mean, you would expect these are, six parameter curves, so you kind of expect them to be large. And we prove a much better band when P is a Cartesian product. This really just comes down to the fact that we reduce the problem to a point line one, and there are better results for Cartesian products for point line ones. But if your curves are a bit simpler, like circles or parabolas or some of the hyperbolas, you can do better. These are three parameter curves, but yeah, we can do a fair bit better. And the technique is a little bit different. And if you're talking circles, the method will require you to assume P is congruent to 3 mod 4, which we put this condition just to not let -1 to be a square. Again, this improves the trivial bounds in such a range. And again, we have better bounds if P is a Cartesian product. So the overall strategy, in the previous simpler argument, we saw that you just sent your curves to lines, and the whole problem just reduced to a point line incidence one. Still, it's very much similar. And I mean, since these linear incidences came about, everyone kind of, if you talk to them, they would say, okay, yeah, you can reduce it to point line, but I think nobody really knew how. And the ideas really came recently from this work of Rudnev and Wheeler. And you'll see this still, I mean, when you see it, it's really simple, but I'd say no one really thought of it. But yeah, the main idea really belongs to Rudnev and Wheeler, who made progress on point modular hyperbole question. The idea is you fix a point in P, and now just restrict your attention to the incidence structure that come from curves passing Q. Then it reduces to a point line one, basically, so on a local level. But for this is for circles, parabolas, and those simpler hyperbolas. But for general conics, the idea is a bit different. You fix 2 points and look at all the curves passing through these 2 points. Then it reduces to a point Mobius transformations incidence problem. Again, locally, I mean, sort of locally, but you still have to go back to all of your curves. And that step is fairly simple. So based on these observations, firstly, we see that by appealing to the linear incidence problem theorems, you can see that there aren't too many curves passing through a single point, a fixed point, or 2 fixed points that have too many points on them. You can then easily go from this to information about all your curves. And specifically, you get a bound on the number of K-rich curves, which is curves in C containing at least K points of P. Ultimately, this information can easily, through a simple counting argument, be turned to an incidence result. So this really is the whole thing, but now we'll slowly go through the details. So CK will denote the number of K-rich curves in your curve set with respect to a point set. So CK is the curves in C so that the intersection of C and P is larger than K. Like we said, the ultimate strategy is to get a bound on these. Now for circles, first, like I said, first we look at this number for the curves that pass through an arbitrary but fixed Q. Now this can be turned to a linear question. But firstly, how do we go from this, let's say, local information to this to something about all our curves? it's just the observation that the curves in C that have more, the K-rich curves in all of our set can be, you sum up the contribution over all such CQK as Q runs through all of P, right? But doing so, because these curves have at least K points on them, you're overcounting by at least a factor of K. So you want to divide by K. That's as simple as this, at least this step. So now let's go and see how do we appeal to linear incidence theorems to bound this CQK. Oh, sorry, first, how do we go from CK to the incidences? So this is just a counting argument. The total number of incidences is just this C equals to K. This subscript equals to K means not just K-rich curves, but curves that have exactly K points on them. Clearly, it's just such curves times K, right? You split it based on some parameter delta with K less than delta and K larger than delta. Now, the first one trivially is bounded by delta, which is the maximum value of K, and the sum over these, which is just C, all of your curves. And this sum, you just partition sort of dyadically. This I is taken from 0, so since P is larger than 2 to the 0 delta, which is just this. And this goes to around log P over delta, so that this upper bound ultimately meets P. But actually, it turns out we can really let this go to infinity, because what we get on the right-hand side converges. So yeah, it's just a base. So these are C's that satisfy this property, and the contribution is 2 to the I plus 1 delta, but we just drag the 2 to this constant over here. So as in the plus 1. And now these curves that satisfy this condition are in this level set really belong to the larger class of 2 to the I delta rich curves. So you just bound this by this sum comes down here, and this becomes, the domain becomes less than the size of this C to the 2I delta, and this stays over here as well. So all that remains, like we said in the previous slide, we assume we get a good bound on CK. You put it in this, and this will be a fraction of a high power of 2 to the I delta. So this thing will actually definitely converge. But like I said, in generally, this will be, the sum will be going ultimately to something like log P over delta. So in general applications, you have that as well. And this sort of, just as a side note, this is a very common technique in additive combinatorics. And I recently saw, a majority of John Bourgain's papers have this technique in them. And I recently saw a paper by Terence Tao, I think the name was something along the lines of the mathematical toolkit of John Bourgain, where he explained basically that there was a fairly limited toolkit that Bourgain used to prove such vast number of results. And he actually has a really nice section about this dyadic decomposition technique. And I definitely recommend you have a look. So this was just a basic counting argument. So now we go, how do we bound CQK, the number of K-rich curves that pass through a fixed but arbitrary Q in P. We just see it for circles because there is a lot more interest in circles, and the argument is very similar to other curves. So a circle will have such a shape originally, and let's say Q passes through it. We do a shift of everything so that we assume Q to be the origin. And By doing so, we have done nothing to our incidence structure because it's just a fine transformation. Now, but with this assuming that Q is 0, 0, I mean the origin, note that this says that the circle must take this form. Why? Because 0 must satisfy this curve. So if you put 0 in here, you get a to the 2 plus b to the 2 equals this thing, right? So, I mean, really the key here is that you turned your 3-parameter curve to a 2-parameter curve. And that was really, this really is the main observation, that now you can appeal to linear theorems. Okay, now we go by the assumption that this C is K-rich, so it has at least K points of P on it. We said 0 is on it, so there must be K minus 1 others. Labeled is as alpha 1, beta 1, up to alpha K minus 1, beta K minus 1. And then this incidence relation can be written as a point line equation. So remember, these alpha 1, beta 1s are all solutions to this. Now these alpha betas become the defining parameters of lines, while these A's and B's become the variables, so the points. So see, A and B is now a point which will satisfy this linear equation. So as in, we sent the K minus 1 points from original problem to K minus 1 lines, and we sent our circle, the parameters defining our circles, to points. And by the assumption that -1 is a non-square, by some calculation, you can show that there is no multiplicity in this definition of these lines. So again, we sent our circles to points, our points to lines. So a K-rich circle is now a K-rich point, as in a circle that had K points on it is now a point that has K lines going through it. This says the same thing. And the thing is, the number of K-rich points can be estimated by point line incidences. So just using the basic identity that if this QK is the number of K-rich points, then the point line incidences is bounded from below by trivially, because we're saying that each point has K lines going through it from L, so it's larger than K times the size of the point set. And you apply existing point line incidences on this, you get something on the right-hand side. You just switch things around, you get a bound on this QK. So a bound on K-rich points gives you a bound on K-rich circles going through Q, and we're basically done. The exact same idea works in higher dimensions as well. So higher dimension point circle incidences turn into hyperplane point incidence problems. And like I said, for large sets, we have good hyperplane point incidence bounds by Wien. We also, for 3 dimensions, we have also one for by Rudnev. But that one, we tried it and didn't give a very appealing bound, and we didn't put it in the paper. There is a good paper on point 3-dimensional circles, I mean spheres. I mean, sorry, I should have said spheres, not 3-dimensional circles, and different things. We're really talking about spheres in higher dimensions. Okay, so how about general conics? These are curves defined by a larger number of parameters. And here the main observation is that a conic, a irreducible conic, is actually a Mobius transformation if these 2 points sit on it. It's fairly simple calculation to see this. You have to write the curve corresponding to a Mobius transformation in its homogenized form, as in as a curve over the projective plane. And when you sub in these points in it, you can see that sorry, you can see that these points lie on it, a Mobius transformation. Also, if you take an arbitrary conic and go by the assumption that these points lie on it, then it's not hard to see that, first of all, it takes the form of a Mobius transformation, and secondly, the defining parameters actually belong to GL2, as long as it's irreducible. So to bound CK, the number of carriage conics, like we said, we take 2 points, and we just want to use this key observation. So basically, once you take 2 points from it, you apply a projective transformation that sends Q1 and Q2 to 0, 1, 0 and 1, 0, 0. So now you can assume that the image of your conics that go through Q1 and Q2 correspond to Mobius transformations. And there is a bound on the number of K-rich Mobius transformation. It was proved recently by Warren and Wheeler, which is the predecessor of our paper, and Warren being one of our co-authors. And again, to go from CQ1, Q2K to just CK, as in from this information about certain conics to all of our conics, again, we want to take the contribution. We go over all 2 tuples of points. We sum up these numbers of CQ1, Q2K. But again, there are K choose 2. These are being overcounted by a factor of K choose 2 because there are these many 2 tuples in each class. So you want to divide it. This for both problems. First of all, this was a relatively simple trick, but it really does feel like there should be better strategies, and actually there is. And we actually, I mean, thank Fam emailed me about this paper of Warren and Wheeler and said, surely there are better ways of doing these points and Mobius transformations. And there was a paper on the reals, and implicit in it was a much better technique. And we wrote a paper, and it came up to a place of applying a point plane incidence. And when you apply it, you get something trivial. And yeah, actually, everything worked out perfectly. It was just that the existing point plane incidences just are not suited for that particular technique. But nevertheless, so yeah, I mean, eventually we came to this sort of more simplistic technique. But it remains a big question. Can you do this better? So you're by doing this step of fixing points, saying something about curves going through this, then doing this silly argument to go back to your curves, this is a big loss. Can you do something more? I mean, somewhat better. And also, so we said things about general conics. We also said things about conics that have 3 parameters defining them. So you might think, well, and we also saw a proof for, sorry.
This would be, I mean, regarding your question, you said in the beginning of the talk that in someone's paper, whose name I can't recall, that there was a method of either partitioning the Cartesian product. Okay, this time, would it maybe, I mean, so the first idea that comes to mind is take the set, the product of P with itself, and try to partition that into pieces and take maxima in smaller pieces, and that would give a better bound, but it would require being able to cleverly partition the point set itself. And I'm not sure if
no, I understand. It actually occurred to us. I mean, so basically we are relying, so we get everything here, we get it better for Cartesian products. Again, just owing to the fact that there are better linear incidence bands for Cartesian products. and they use the same technique. So the question is, would doing this for conics do better than what they did for lines? Maybe not. But yeah, this did come up, and we didn't spend a lot of time considering.
The other idea that comes to mind is considering maybe the transformation on the set of points, and maybe approaching it through some sort of something resembling representation theoretic idea of a group acting on the set of points and using some maybe invariance to improve the bound, but not sure if.
I should say the second technique sounds a lot like something we actually did try, that I said this brings the two-dimensional problem to requiring something about three-dimension linear incidences. And the thing is, what is known for point plane incidences didn't give something non-trivial. I mean, when you look at the proof of how they go from point plane to point line, yes, something very strange is happening when an incidence band that really just works for sort of balanced point sets and plane sets suddenly is allowed to say something really strong for unbalanced two-dimensional problems. I mean, what you said, yeah, I mean, there is actually a paper that looks at this group theoretic sort of approach, but yeah, we did try it and didn't work. But yeah, I mean, I definitely welcome any ideas of approaches, or because like I said, this is a really silly approach. But yeah, I'm not really sure. This was really the best we could do, and we weren't that happy. So, I mean, I'm not sure if I answered you.
I mean, that does answer. And at the moment, no ideas come up better. But I mean, it seems like also if you want to bound the sum, probably choosing maximum is probably
it's
the best
very
way
bad.
to go if you don't want to individually compute the individual components.
Exactly.
If you just want a bound, that's may be almost the best thing one can do, maybe. I don't know.
Yeah.
I'm not sure.
Yeah, it is a ongoing sort of.
What was that? Huh?
Yeah, I'm muted. But yeah, I'm not, I mean, there are other approaches, but just even these linear, I should say these point plane incidence of rootnet actually relies on the progress that was made on Guth-Katz resolution of Erdős's distinct distances problem. We'll see it in the next slides. And so, you know, the machinery there, I mean, good luck sort of making progress on that. As in, it relies on very heavy machinery. So really, one way we see progress over here is to improve point plane incidences. And I'm saying, yeah, I don't really, it is a difficult problem. Okay, so one application for what we did, especially these point circles or point spheres problems, is the Erdős distinct distances problem. And so let's first look at what the problem is. For 2 points in the plane, recall the Euclidean distance is defined as such. And the set of distances formed by points of P is just a set of distances determined by two totals of points in P. And we are interested in getting lower bounds on this distance set. Erdős conjectured that it should be linear essentially in the size of P. And he actually gave an upper bound of this order. So this should be basically the conjecture. And using polynomial methods, Guth and Katz essentially resolve the conjecture, but there is still a gap in the logarithmic factor. So again, I mean, I'll wait another couple of seconds. So the distance, the size of the distance set determined by a point set is the distances between two tuples of points, the number of such distances. And we expect it to be at least this big. And you can also look at the pinned distances problem, which is the number of distances formed by points of P pinned at a fixed point Q. So this time we're not going through two tuples, we are taking one Q and looking at the distances formed by other points of P and Q. And the pin distance set is the maximum of dpq as Q runs through P. Same conjecture exactly as first conjecture of Erdős can be asked about this pin distances problem. This is largely open, and the best band was from 2004 of 0.86 by Katz and Erdős. Recently, Murphy and et al. Proved that if you work over arbitrary fields, and the proof also works for finite fields, then you get the 2/3 for the pin distances problem. Also worth noting, the pin distances is a superset of the distances problem. So as in, if you get a bound here, you obviously get a bound on the distance problem. And this is very recent, and this is the best known. And also they don't have this P congruent to 3 mod 4 in their statement, but it was just easier to say it like this, because then when you have isotropic lines, the statement becomes a bit more complicated. And there's also the finite field Packliner type questions that ask, working over finite fields, how large should your point set be so that your distance set becomes essentially all of Q? So distance set obviously is a scalar and belongs to FQ. So how large should your point set be in the plane so that the distances formed by it fill up the whole FQ? And Chapman and others showed that if P is larger than Q to the 4 and 3, then you have this result. Then Bennett and others proved the same result, but for the pin distance version of it. And the conjecture would have been that as long as P is slightly over Q, so note that P could go up to Q to the 2. But P, as long as it's a bit larger than Q, then you should have this. I mean, I think this was roughly the conjecture, but it's strange that very recently, Murphy and Petridis actually showed that 4 on 3 is sharp. And this comes down to existence of a lot of vector spaces in FQ. But the conjecture remains that if you're working over FP, so Q is a prime power. If you're working over FP, you should still have the result as long as you go a bit over P. And in the same paper, Murphy and others in the recent one, they showed that this 4 on 3 can go to lower to 5 on 4 as long as you work over prime order fields. Strangely enough, Falcon is actually a question over the reals, that if Borel sets of high Hausdorff dimension should have a dense distance set, and this 5 on 4 actually shows up there as well, with two fairly different problems. And one observation is that this distance, I mean, distances over finite fields don't make a lot of, don't have the same Euclidean meaning anyways. And the distance between 2 points P and E is really the image of P minus E over a function, this x to the 2 plus y to the 2. So, I mean, it's very natural to ask, what can you say about the other choices of F? And not much was said until our recent paper, we're able to say non-trivial statements about all these choices of functions. And these actually have geometric meanings as well. This is the Minkowski distance and parabolic distance, but again, over reals, not over finite fields. Over finite fields is just an algebraic quadrature. Again, E has to not be the whole plane to have something non-trivial. And it's interesting that even though our techniques look so ridiculously inefficient, we actually reproduced some other techniques that actually landed on 8 on 15. But this was improved in a series of papers until this 2021 paper that they got 2 on 3 for when f is this normal distance function. But those techniques don't work for these other choices of polynomials. So, I mean, the idea, I'll just, I mean, let's look at the geometric idea. So basically, the distance problem, you can take a circle set that has radii coming from your distance set. So the distance set is the size of the distance set is the indeterminate that you're trying to find. So take a set of circles that have radii, this t, coming from your distance set, and centers coming from your point set. Now, for each point set, there should be at least p incidences, right? P as in, or rather E incidences, because these circles have radii coming from your point set, so they are meeting all your points at any given point. So as you let P to run over your set, so the number of incidences is actually e to the 2. So the number of centers times the number of I mean, like we said, for a single point center, you get at least E incidences, and there are E centers, so e to the 2. And this was the geometric idea of when f was the normal, I mean, x to the 2 plus y to the 2, but the same works for other functions as well. So the upper bound for your curves, your conics, is a number of centers times the number of times the maximum of the radii, which is, you know, the distance set that you're actually trying to find a lower bound for. Combine an upper bound that you get for this incidence, that you get it from our result for point-conic incidences, with this lower bound, and you get the required upper bound for these pinned algebraic distances. This was also a very standard argument. It was actually one of the early arguments for progress over the Erdős distances problem. You could do exactly the same techniques for higher dimensions as well. Like I said, point spheres can be translated to point Harper plane problems. And you can actually go a step further and consider distances formed between 2 point sets. So E coming from one point set and F coming from another. And Sparlinski, Igor, proved the lower bound using character sums that basically this gives that if product of EF is larger than Q to the D plus 1, then the distance set fills up the whole space, all of that Q. And so, for example, if you take D to be 2 over the plane and E and F being the same, this gives 3 on 2. But we said 4 on 3 is actually known for Falconer type questions. There were some improvements. The bounds are a bit of nightmare, and these allow for different ranges of E and etc. Again, the techniques are free analytic, and for odd, they got this. And I mean, I won't do a full band analysis. And for D being even, the problem was that, you see, this is essentially the same thing, but the Fourier analytic techniques didn't quite work well for D being even. So they have this extra assumption. Now, the point really just that I wanted to make is that, again, if our techniques looked ridiculously inefficient, we actually recovered this. And we didn't have this extra assumption that EF being larger than Q to the D. I mean, this was interesting. Like I said, the method was pretty inefficient. So maybe it gives a clue for further improvements if you can improve the techniques. And I only wrote this as you get different ranges and whatnot, how you get improvements. But I wrote this one particular because it's the same bound here. If you take E and F being the same, it's exactly this one for this range. The point again being that we don't have this extra assumption. And with that, so yeah, I mean, this comment. And with that, I thank you for your attention.
Okay, thank you. You may unmute your microphone and join me for clapping to Dr. Ali Mohammadi for his excellent talk. Any question?
Was there at some point in the talk sort of a attempt at generalization by taking more than one point on the curve, or taking a certain finite number of points on the curve, and defining the incidence relation that way, and finding bounds? Or is the problem at hand already, when it's only one point, is there already unsolved problems that, considering the generalization, is too much of an outreach? Or are there people that also consider looking at such generalizations?
Well, see, for linear problem, I think, say three points being on a line, three tuples of points being on, those are just collinear triples. And these are well studied. Also for finite fields as well, collinear triples and collinear quadruples are well studied. But I mean, what I showed you is really one of the early instances of the nonlinear, I mean, progress over nonlinear questions. So for curves, not really, no. So four tuples of points lying on curves, I don't think so. Certainly something you can consider, yeah, and I think it should be doable.
Do you think that would make the problem, that's a simpler problem because of higher constraints?
Actually, over reals, banding the number of, for example, collinear triples is essentially equivalent to incidences. It's not easy to trivial to see, but yeah, people have shown up to logarithmic factors is the same thing. And it's interesting that so over the reals, the best incidence bound gives you a sharp band on the number of collinear triples. And you can also go from that bound to an incidence bound using Holder inequality and whatnot. But over finite fields, the best known incidence bands actually give you a sharp band on collinear quadruples. But yeah, and same, you can go back and forth between the two theorems. So they're not easier or harder. The higher you go, yeah, the problem becomes easier. And one of the top problems in additive combinatorics now is to prove sharp bounds for collinear triples. which would be equivalent to getting a sharp bound for point line incidences. But going back and forth between, I mean, quadruples of rational points on curves and whatnot. Yeah, I think I'm not sure. Yeah.
And also in the bounds, the size of the field does appear, right? And is there what sort of a relationship was it? It's a q to some power appears in the bound, and is there, when you consider the embedding of the one field into the other, is do these, are the inequalities, is there a constraint coming from field embeddings?
I'm not sure. Do you mean this appearance?
Well,
basically, you can make this statement that P is in any arbitrary field, and these things are true. And if the characteristic is P, then you need this assumption.
okay.
So, I mean, if you work in FQ, characteristic P, same assumption. And actually, one of the top questions is giving a better characterization, not asking your P to be so small. As long as P doesn't correlate with these Cartesian products of subfields, you should have a non-trivial bound here. That is one of the top questions in this area. I'm not sure if that was along the lines of what you, because the only appearance of P is actually here. The characteristic.
Yeah, okay. I see. I mean, this is the latest result and the main focus right now.
Yeah, and
I was referring to, maybe, was it again point-conic? Maybe the first slide had FQ in it, but I mean, it won't be relevant for here, but yeah, here.
Okay.
No, maybe not. I don't know.
Maybe here.
Yeah, whenever we're not considering things over FP, but over, I mean, the characteristic is P, but the field itself is P to the N for some N. And we're considering the incidence relation over FPN for one N and then for another N. And then we're looking at whether the two inequalities have a dependence, and we might distill or reduce the question something independent on. And that's what I meant. How
I mean, it really is still in C. Here we take F to be arbitrary, right? So it really is independent of, it is just dependent on the characteristic.
Okay.
And like I say, see, this condition here is essential to make sure that P doesn't fill up the whole FP2. Or even if you're working over FQ, this is just saying that don't allow P to be too close to Cartesian product of two subfields. But this is a ridiculous assumption. And there is actually a result of mine that gives a non-trivial point line incidence bound as long as you don't have large intersection with affine images of Cartesian product of subfields. But their bound there is really weak. It's just barely non-trivial. But yeah, it is one of the top questions to drop this condition and say, prove something like this under the assumption that P doesn't correlate largely with affine images of Cartesian product of subfields. Because if that's the case, then you can only get a trivial bound. But yeah, as far as your question of N goes, yeah, it's already independent.
Okay. But I mean, well, but in that case here, F is just a characteristic of P, but of arbitrary, it could be of any finite size, or it could be even the closure of all.
Yeah. It could even have characteristic 0, in which case you don't care about this. But the thing is, characteristic 0, you generally don't care anyways, because there are, for example, over R, there are better bounds, over C, there are better bounds.
Okay, okay. Thank you. Oh, okay. Maybe let me try to rephrase it. So could we possibly partition the incidence set depending on points that fall inside a certain FPN and obtain different bounds, and then take a limit over all possible n or something like that?
Well, I mean, when you say get the bound for points lying in FPN, what bound would you want to use? I mean, you would still be using this, right? Which is independent of n anyways.
Okay.
I mean, I'm not sure, maybe, I mean, are you thinking of a strategy for general improvements, or I mean, getting this to work over?
No, maybe what I'm saying is irrelevant. I mean, I don't completely, I'm not even convinced myself now. I was just thinking maybe if we partitioned, or if we required, so independent on n, you're saying that the bounds we already have are, well, the size of P and the size of L are still going to be dependent on which finite field you look at, won't they? They will grow together with them?
No.
Okay.
Yes and no. I mean,
okay.
As long as they're finite and, you know, sure, I mean, they would be bounded from above by the size of your space, surely, but doesn't matter when you're talking about upper bound.
Okay.
But yeah, I mean, it again, to emphasize, it is one of the top questions to drop this condition and say something a bit more for FQ. Very, very good question. I mean, I think it will get serious attention if someone gets, I mean, transfers these results, same style of results, to those type of questions. Even very, very simple geometric questions like, if you have a point set, how many directions does it determine? Now, if this point set is taken to be in FQ, again, you don't want it to intersect largely with Cartesian product of subfields. And even in this setting, pretty much nothing is known. Even this is a very simple geometric question, and still for FQ, nothing is known for pretty much, and for FP, sharp results are known. Even for FQ, if the size of your point set is exactly Q, something is known. If it's Q plus 1 or above, then there is a one-line proof of pigeonhole showing that it must fill up the whole space, the direction set. But no, if you go Q minus 1, pretty much nothing is done. Well, actually, Q minus 1 is done. It's, you know, seriously small sets now.
Ali, in some of the results, you have this condition that P should be free mod 4.
Yep.
Is it really necessary, or just the proofs don't work well enough?
It showed up when we wanted to show the correspondence of circles and, I mean, the correspondence between the point circle and point line problem. It shows up there. So you want these lines to be defined with that multiplicity. When you want to show that, for example, alpha 1 plus beta 1 and so on equals to another line defined by alpha 2, beta 2, in showing that, therefore, these alphas and betas must be equal, there you need that minus 1 is not a, because of this thing, that minus 1 is a noise square.
Okay.
So only circles, not parabolas, not other conics or hyperbolas.
Okay, so you see, this condition is really necessary. It's not just an artifact of the proof.
Yeah, I mean, you could maybe, I mean, for example, for general conics, we didn't put this condition, but you get a weaker band. So yes and no. And frankly, another option is to just see, okay, minus 1 is a square. What can we say? We didn't really, we kind of took the lazier path. Maybe you can, yeah.
Okay.
Okay, any question? Okay, if there are no questions else, I say thanks again to Dr. Mohammadi for his excellent talk, and thank you all for attending this session. Before ending, I should mention that our next speaker is Professor Dabruksi from Poland. I am apologize if my pronounce is incorrect. So I hope to see you all there. I mean, at 2 weeks later from now. Thanks again for attending, and I should stop the meeting. Bye bye, everyone.
Thank you. Bye.
Thank you, Dr. Mohammadi. It was excellent.
Thank you.